Hello. In the previous video, we defined what a group is. We've seen some basic examples that come from numbers, and we also described some of the basic properties of group operations. In this lecture, we want to study the symmetric side of groups, which is the main motivation of defining groups. So here is a meta example of groups. Suppose X is any object. You can think about geometric objects like triangles or polygons, or you can think about algebraic objects like vector spaces, or you can think about combinatorial objects like graphs. X is one of these objects. By a symmetry of this object, we mean a bijective function from X to X, which preserves properties of X. For instance, if X is a graph, by properties of this graph, we mean that vertices are sent to vertices, and if two vertices are connected to each other through an edge, then when we send them by F, when I send V by F to F of V and W to F of W, V and W are connected to each other precisely when F of V is connected to F of W. Or when X is a linear space, then F preserving properties of this linear space essentially means that it's a linear function. Now, whatever that means, in each case, we are going to look at it separately. So when we say F is a symmetry, it is bijective and it preserves properties of X. Now, if we collect all the symmetries of X in a set and call it sim of X, then this sim of X has the following properties. If I give you F and G, both of them are symmetries of X, after I compose F by G and look at F of G, that would be another symmetry of X, because composite of two bijective functions is again a bijective function. And if F and G, both of them preserve properties of X, then their composite also preserves it. That's quite an intuition in general. Now let's see other properties of composition of functions. So of course, composition of functions is associative, meaning FOG OH is the same as FOGOH. The main reason being that both of them, when I apply, so both of them are functions, bijective functions. When I apply them to a point small x, this side means FOG of H of X, which is the same as saying that it is F of G of X. The same is true for this is for this is for this. Okay. The same is true for the other side. This is precisely FOGOH of X. So these are the same functions. They have the same domain, they have the same codomain, and they have the same rule. We also notice that identity, of course, preserves properties of X, and it is a bijective function. So it belongs to the set of symmetries of X. And when I compose F by identity function or identity by F, I end up getting the same function F. F being bijective is invertible. So there is the inverse function from X to X. And if F preserves properties of X, F inverse should also preserve properties of X. Therefore, its inverse is a symmetry of X as well. And we notice that F inverse OF by definition is the same as F OF inverse, and that's the identity function from x to x. So altogether, we are saying that the set of symmetries of X with the composition forms a group. It is closed undertaking this, and therefore composition forms a binary operation on the set of symmetries of X. Composition has the associativity property, is associative. We have the neutral element identity. Every element has an inverse, so it forms a group. This meta examples is the main source, is the main reason that we actually have group theory, in a sense. Group theory is designed in order to study this type of groups mainly. Okay, now let's look at specific examples and see what we can say about the structure of the groups. So here is the initial example where we don't put any particular structure on X. X is just a set, just a non-empty set. We don't demand any particular structure on X. In that case, every bijection from X to X is considered a symmetry of X. This takes us to the following definition. If X is a non-empty set, then the set of all the bijections from X to X is denoted by S sub X. And a particular case of this, when X is only the interval consisting of integers from 1 to n, 1, 2, 3, n, then instead of writing S sub this set, we simply write S sub n. So S sub n consists of bijections from this set to itself, which is an alternative way of saying that S sub n consists of all the permutations of 1 to n. Okay, following the same meta example that we had, if we look at S sub x and use composition, we end up getting a group. So if I give you F and G, two bijections from X to X, FOG is simply the composite of F and G. S sub X with composition is called the symmetric group of X. In this case, we say it is the nth symmetric group. Okay, so let's quickly check some of these properties. Some of them we are not going to prove now, and I refer it as an exercise. You have seen it earlier in your earlier courses. In UCSD, of course, we covered these type of results in Math 109. What is the first step? The first step is to show that composition is indeed a binary operation on the set of bijective functions. That means we need to show that composite of two bijections is a bijection. And this is what I'm saying that we usually cover in UCSD in Math 109. So composite of two bijections is a bijection. Therefore, composition does indeed define an operation on S sub x. Next, we notice that composition is associative, and this is exactly the type of computation that I have done earlier. When I apply the function FOG OH to x, that by definition means FOG applied to h of x, and that means f applied to g of h of x. Now, if I look at the other side of the associativity equation, FOGOH is the same as f of GOH applied to x, and GOH means g of h of x. So we reach to the same value. So both of these functions, f(o)(g(o)h) and f(o)(g(o)h), both of them are functions from x to x, and they are giving us the same rule. Therefore, they are the same functions. Identity is a bijective function from x to x. Therefore, it does belong to the symmetric group of x. For every function from x to x, composite of identity and f is the same as composite of f, and identity n is the same as the function f. Therefore, the identity function is the neutral element of the symmetric group of x. We haven't proved that it is a group, but nevertheless, let's call it symmetric group of x. It's a neutral element of the composition operation. And finally, because f is, so every element of a sub x is a bijection, then every element is invertible. In fact, this is another result that we usually cover in Math 109, that a function from x to y is bijective if and only if it is invertible. So knowing that f is bijection, we can deduce that there is f inverse from x to x, so that f composed with f inverse is the same as f inverse composed with f, and that's the identity function. That's the same as saying that f has an inverse with respect to the operation, with respect to the composition as an operation. Altogether, we have proved all the properties of a group. Let me finalize and let me make sure that we also pay attention to this remark, that when I have these equalities, we can deduce that f inverse itself is also invertible, and therefore it is bijective, and so it does belong to S sub x. Because it is important to point out that the inverse that we are finding also belongs to the set that we have been studying. So altogether, we get that the symmetric group is indeed a group. Now, let's define an abelian group. A group is called abelian if for every two elements that we pick from this group, g1 dot g2 is the same as g2 g dot g1. When I can commute elements under the operation, when I can switch the order of multiplication, then we simply call the group abelian. For instance, all the groups that we discussed in the previous video, when they came from numbers, all of them were abelian, like the ring of the additive group of integers, or the group of units of integers mod n, or complex numbers under addition, or non-zero complex numbers under multiplication. All of these examples are abelian. But next we will discuss that a symmetric group is not abelian as soon as X has at least 3 elements. Abel was a mathematician who was studying zeros of polynomials, and he observed that if symmetries of zeros of polynomials, after we add them, the system of numbers that comes out of zeros of a given polynomial, if the symmetries is abelian, then you can actually solve that polynomial equation using radicals, addition, subtraction, multiplication, and division. Later, Galois studied that further and again used symmetries of system of numbers that comes out of zeros of a polynomial to give a necessary and sufficient condition under which one can solve that polynomial using radicals, addition, subtraction, multiplication, and division. You will learn about this if you take the 100 series. Okay, so let's see why the symmetric group is not abelian when I have at least 3 elements inside the set. I'm going to discuss only the case of S sub n, but the general case is rather similar. So the claim is that S sub n is not abelian if n is at least 3. That means I need to produce 2 elements inside S sub n so that F1 O F2 would be different from F2 O F1. Okay, so elements of S sub n are permutations of 1 to n. They are bijective functions from the set 1 to n to the same set. The first one just switches the order of 1 and 2 and doesn't touch the rest. So f sub 1 of 1 is 2, f sub 1 of 2 is 1, but then I'm fixing the rest. The rest are not changing at all. Now, the second function switches 1 and 3. So f sub 2 of 1 is 3, f sub, here is 2. F sub 2 of 3 is 1, but I'm not touching the rest. So the first one just switches the order of 1 and 2. The next one swaps the order of 1 and 3. But the rest are going to be the same as before. My claim is that in that case, the composite of F1 and F2 is not going to be the same as composite of F2 and F1. To show that these two functions are different, it's enough to check that they are different at a single value, and that value is 1. We are going to show that F1 or F2 of 1 is not the same as F2 or F1 of 1. Okay, let's see why this is the case. F1 O F2 of 1, what is this? It is F1 of F2 of 1. F2 sends 1 to 3, so F2 of 1 is simply 3. And F1 fixes 3, so F1 of 3 is simply 3. So the value of this function at 1 is going to be 3. Now let's see how about the other way. F2 of F1 of 1 is what? It is F2 of F1 of 1, but remember F1 of 1, F1 swaps 1 and 2, so that would be F2 of 2, and F2 of 2 is fixed by F2, so we get 2, and these are not the same elements. So F1 of F2 is not the same as F2 of F1, and therefore S sub n is not abelian. As we can see, I mean, most of these symmetries are, I mean, if we think about groups as symmetries, they are often non-commutative, okay, but often needs to be quantified in a proper way in order to say this. But nevertheless, you can imagine that if I give you an object and I ask myself what are the symmetries of this object, most likely we should be able to find 2 symmetries that do not commute with each other. After all, we are looking at composite of functions. And what are the chances that we should be able to switch, we would be able to switch the order of these functions and ending up getting the same function? This is just intuition. There is no math content in what I just said. Okay, now let's see how many elements the symmetric group, the nth symmetric group, has. Every element of S sub n is essentially a permutation of the points of the elements 1, 2, n. We are looking for bijections from this set to itself. Now, how many possibilities do we have for f of 1? Okay, f of 1 can be any of these numbers 1 to n. So f of 1 has n possibilities. Now, if I fix f of 1, then f of 2 can go to any of these values except f of 1. That means f of 2 has n minus 1 possibilities. Now we can choose any of these for f of 2 and then continue like that. Then f of 3 can be anything from the numbers 1 to n except f of 1 and f of 2. So there would be n minus 2 possibilities for f of 3. And then I continue like this, and finally for f of n, I would have only one choice because n minus 1 of the numbers from 1 to n have been already taken. So then if I use the multiplication principle, altogether we get n times n minus 1 times n minus 2 times 2 times 1 possibilities for the function f. That means the symmetric group, the nth symmetric group, has precisely n factorial number of elements. Okay, now, so far we studied the case where we did not impose any property on the set X, and we just asked what are the symmetries of a set X, and we reached to the symmetric group of X. Now let's see an easy graph. I give you an n cycle. I give you an n cycle and I ask what are the symmetries of this n cycle. When I say n cycle, it likes this. So I have n vertices and I connect them one after another. So as we can imagine, so that would be our n cycle. And we are asking what are the symmetries of this n cycle. Again, what do we mean by symmetries of a graph? By symmetries of a graph, we mean, so before I go to the labeling of this graph, by symmetry of a graph, we mean a bijection from the set of vertices. So let's say V is the vertices of this graph. By symmetries of this graph, we mean a bijection from the set of vertices to itself, so that for two vertices, V is connected to W, this is an edge, if and only if f of V is connected to f of W. So if edges are going to edges and that's it, then we call this a symmetry of this graph. Now, we are given this graph here, and for our argument, it would be nice to label this graph using elements of Z sub n. We are going to label it using this group, Z sub n, this set, the set of integers modulo n. So, and I'm going to label them one after another by elements of Z sub n. So that would be the residue class of 0, then residue class of 1, residue class of 2, and so on. So there are n of them, as we have proved. And each one is connected to the next one in this set of integers modulo n. So to be more precise, the residue class of I is connected to exactly two residue classes. One of them is residue class of I minus 1, and the other one is the residue class of I plus 1. Okay, now following the meta example, we should be able to show that symmetries of a graph G with composition is a group. So again, composite of two bijections is a bijection. When I connect to, when I preserve edges, then the composite should also preserve edges. Okay, so here we are more interested in describing elements of symmetries of the n cycle. Okay, look at this graph. The first thing that we notice that every vertex looks like any other vertex. What do we mean by that? I can rotate the whole cycle and send 0 to any other vertex, And by rotating, I'm not changing the structure of the graph. If two vertices are connected before rotation, then they are connected after rotation. Rotation is indeed a nice symmetry of this graph. But we can also describe it using addition inside the set of integers modulo n. So let's consider one-step rotation, and let's call that sigma. What do we mean by one-step rotation? I'm sending the residue class of 0 to residue class of 1, and residue class of 1 to residue class of 2, and so on. That means if I use addition in the set of integers modulo n, I'm essentially giving you a function from the set of integers modulo n to the set of integers modulo n, and I'm adding the residue class of 1 to x. So you give me x, I just add residue class of 1. That's essentially this one-step rotation. Now let's see why it's a bijection. Why is this a bijection? Because I can undo adding this residue class of 1 by adding inverse of residue class of 1. So if instead of adding 1, I add -1 or residue class of -1, I'm undoing what sigma does. That would be inverse of sigma. Because sigma has an inverse, we deduce that sigma is a bijection. So sigma is a bijection from the set of vertices to itself. And next, I want to argue why it sends edges to edges. Okay, so to make the argument precise and not just refer it to the picture, notice that x is connected to y, the residue class of x. So x and y, both of them are elements of the set of integers modulo n. Then x is connected to y precisely when their difference belongs to this set. So it's either residue class of 1 or residue class of -1. Remember, I is connected to exactly two vertices. One of them is the residue class of I minus 1, and the other one is residue class of I plus 1. So this means if this is connected to some other residue class, then their difference is either residue class of -1 or residue class of 1. That's exactly what I wrote over here, that x is connected to y exactly when their difference is in the set, the residue class of 1 and residue class of -1. Now, when we apply sigma, let's see what happens to the difference. Sigma of x minus sigma of y, okay, so each one of them have been added residue class of 1. So those residue classes of 1, they cancel each other. So we end up getting that sigma of x minus sigma of y is simply x of x minus y. Now, if x minus y is inside this set, then so is sigma of x minus sigma of y. If sigma of x minus sigma of y is inside this set, then so is x minus y. That means if x is connected to y, then sigma of x is connected to sigma of y. And if sigma of x is connected to sigma of y, then x is connected to y. That's exactly what we needed for sigma to be a symmetry of this graph. So sigma is indeed a symmetry of this graph of the n cycle. And we use this exponent notation, and when I apply sigma I times, that means each time I'm adding the residue class of 1, residue class of 1, and so on, at the end I'm adding residue class of I because I'm adding 1 I times. So sigma to power I is essentially a rotation, I times rotation, I times clicking it to the left, counterclockwise rotation. In particular, when I apply this to the first vertex, the residue class of 0, I end up getting the ith residue class, the residue class of I. That's exactly our claim, our initial claim, that we can send every vertex to any other vertex. We can send the vertex labeled by the residue class of 0 to an arbitrary vertex that's labeled to the vertex that's labeled by the residue class of I for an arbitrary integer I. Okay, now in order to understand symmetries of this graph, so far we understood where we can send this first vertex. Next, we are going to assume that I'm going to fix this vertex. And we ask ourselves, what can we do with other vertices? This is a common technique that we use in order to understand symmetries of objects. It's kind of similar to what we did with the symmetric group when we wanted to understand number of elements in the symmetric group. So there, first we ask, where can we send 1? We realize it can be sent to everything. Then we ask, okay, now if we fix 1, then what happens to the rest? It's a similar idea here. First, we discussed where we can send the vertex that is labeled by the residue class of 0. Next, we asked, what can we say about symmetries that fix the vertex that's labeled by the symmetric group, by the residue class of 0? So we are asking, what are the symmetries that do not move the vertex that's labeled by the residue class of 0? So gamma is a symmetry, and gamma of the vertex that's labeled by the residue class of 0 is the residue class of 0. Now, because gamma is a symmetry, the neighbors of this vertex are supposed to go to a neighbor of this vertex because this vertex is fixed. So again, here is my graph. This is my 0. It has two neighbors. One of them is 1, is labeled by 1. The other one is labeled by -1 or n minus 1. If I fix this one, so of course the graph goes like this. But if I fix this one, then these two vertices have two options. Either I have to fix them, I have to send this to itself, or this needs to be sent to another neighbor of the vertex that's labeled by 0. So gamma of 1 is either 1 or -1. So because gamma of 0 is 0 and gamma of 1 is supposed to be connected to gamma of 0, then gamma of 1 is either 1 or -1. Now, we are going to consider two cases. The first case where gamma of 1 is 1, and the second case when gamma of 1 is -1. And in either case, we are going to determine what gamma is. Let's start with a case where gamma of 1 is 1. So we are fixing both 0 and 1. Both of them are fixed. Now I'm asking, what can we say about the rest? If you think about it, if I give you a ring and I fix 2 points, then it's quite rigid. I cannot move the rest at all. And that's exactly what we want to show, this type of rigidity. So if we fix 2 of them, then the rest are going to be fixed. That means gamma is going to be identity. So that's our next claim, this type of rigidity. So if gamma is a symmetry of the n cycle, and it fixes 0 and 1, 2 consecutive points, then gamma is identity. Okay, so let's show this. What does it mean that it is identity? It means gamma of the vertex that's labeled by the residue class of I is supposed to be residue class of I for every I. And we are going to show this equality by induction on I. So we need to show that gamma of the residue class of I is equal to the residue class of I for every I. And we are going to show this by induction. Of course, by hypothesis, we already have it for I equals to 0 and 1. Either we can use two-step induction or we can use a strong induction hypothesis. In either way, it's a type of induction. Here I'm using a strong induction. Maybe it was better to use two-step induction. Okay, so by the hypothesis we have the base case. So let's look at the induction step. What does that mean? In the induction step, we assume that what we want to show is true for all the integers that are at most k, and we want to go one further step. That means we have to show that gamma also fixes the vertex that's labeled by k plus 1, the residue class of k plus 1. Now, let's look at the last vertex before k plus 1. That's the residue class of k. This vertex is connected to two vertices. One of them is k plus 1. The other one is k minus 1. Now, when I apply gamma, these edges are supposed to go to edges. So gamma of k is supposed to be connected to gamma of k plus 1. But again, gamma of k is k. Therefore, gamma of k plus 1 is supposed to be connected to k. That means gamma of k plus 1 has two possibilities, is either k minus 1 or k plus 1. But we claim that it cannot be k minus 1. Why is that? Because again, by the strong induction hypothesis, I know that for all the numbers that are at most k, I have this equality. In particular, I know gamma of k minus 1 is k minus 1. So gamma of k minus 1 is k minus 1. Gamma is a bijection. So no other vertex is allowed to go to k minus 1. In particular, gamma of k plus 1 is not allowed to be k minus 1. So gamma of k plus 1 is not allowed unless k plus 1 is k minus 1. In that case, n is 2, and then it's fine, and so on. So let's focus on the more important case where k plus 1 is not k minus 1. If they are the same, then of course then our claim is still true, because gamma of k minus 1 is k minus 1 anyway. So if they are the same, again, I wrote it over here. If they are the same, then gamma of k plus 1 is gamma of k minus 1. And then in that case, by the strong induction hypothesis, that's k minus 1, and that is k plus 1. If they are not the same, then gamma of k plus 1 is not gamma of k minus 1. And gamma of k minus 1 is k minus 1. That implies that gamma of k plus 1 cannot be this one. And so it should be this one. And that's exactly what we wanted to show. So in that case, again, if k plus 1 is not k minus 1, their gamma should be different. So gamma of k plus 1 cannot be k minus 1. And from there, we deduce that gamma of k plus 1 should be k plus 1, because it cannot be k minus 1. It should be k plus 1. And that's exactly what we wanted to show. Now, by induction, we deduce that there is a unique symmetry of the n cycle that fixes both 0 and 1, and that is identity. Okay, now let's go and let's look at the case. Let's look at the next case where 0 is fixed, but 1 is sent to -1. In order to understand those symmetries that fix 0, and send 1 to -1, we start with one example. If you look at this picture, reflection about this line, let's say, sends 1 to -1 and 2 to -2 and fixes 0 and so on. Now, if we use labels that we have used using integers modulo n, this reflection can be given by this function tau from z sub n to z sub n that sends x to -x. Again, let's see why it's a symmetry of this n cycle. The first thing that we notice is that it is in fact a bijection because tau of tau is identity. If I apply tau twice, I get this, which is identity, which is x, and therefore this composition is identity. And so tau is indeed a bijection. The next thing that we notice is that tau of x minus tau of y is y minus x. So I'm essentially negating the difference. Now, again, let's recall that x is connected to y precisely when their difference is inside this set. And this set is symmetric, meaning if I take an element, then its inverse is here and vice versa. So this means if y minus x belongs to this set, then tau of x minus tau of y belongs to this set. Okay, if x minus y belongs to this set, then negative of that, which is y minus x, is also inside this set. That means tau of x minus tau of y belongs to this set, and vice versa. That means this difference is inside this set precisely when tau of x minus tau of y is inside this set. And being inside this set means x is connected to y, and therefore we deduce x is connected to y if and only if tau of x is connected to tau of y. That means tau is a symmetry of this. Again, here I pointed out that tau squared is identity, and therefore tau is a bijection. Therefore, tau is a symmetry of the n cycle. And this is a symmetry that sends 1 to -1 and fixes 0. Now, our next claim is that any symmetry that sends a 1 to -1 and fixes 0 is tau. There is a unique one, and that is tau. That's our next claim. Okay, so if gamma is a symmetry of the n cycle, and it fixes 0 and sends 1 to -1, then gamma is just tau. The technique of the proof of this claim is quite interesting and quite general. In the previous claim, we proved this type of rigidity, that if we fix 2 consecutive points in this graph, then it should be identity. Now we are going to use that rigidity in order to show this claim. How do we do that? We look at the composite of tau and gamma. Notice both gamma and tau fix the point 0. Therefore, the composite also fixes the point 0, because the composite is tau of gamma of 0, but gamma of 0 is 0, and tau of 0 is 0. So the composite also fixes the point 0. Now, how about what composite does to the point 1? Gamma sends 1 to -1. Tau brings it back to 1. So tau, the composite of tau and gamma, fixes both 0 and 1. And it's a symmetry of the n cycle because it's composite of 2 symmetries. Therefore, by the previous claim, by the rigidity that we proved, it is the identity. So that means tau composed with gamma is identity. Now we can bring this tau to the other side. And whenever we say bring tau to the other side, it means we are multiplying both sides by the inverse of this element from the appropriate direction. So we multiply both sides by tau from left to cancel it out. because tau is in inverse of itself. So by applying tau to both sides and changing the order of parentheses, it's associative, so I can do that. Tau composed by itself is identity, and tau composed with identity is tau, and this is just gamma, so we deduce that gamma is tau, as we claimed. Now we have a complete understanding of symmetries that fix the point zero. So either it's identity or it's this tau. Knowing this is enough. Knowing this, coupled with the fact that zero can be sent to any other vertex using powers of sigma, knowing these two facts are enough to describe all the symmetries of the n-cycle. Okay, let's see. Claim is that every symmetry of the n-cycle is given by one of these elements. It's either identity or a power of sigma, not every power, only the first n-1 powers. Or when we apply tau to these powers, so tau applied to identity is just okay, or maybe we apply the sigma i's to tau. So identity applied to tau, we get tau, sigma applied to tau, sigma squared applied to tau till we apply sigma to power n-1 to tau. We end up getting 2n elements, and these are all the elements, all the symmetries of the n-cycle. And in fact, all of these are distinct. Okay, let's see why this is the case. Let's start by proving why these are all the symmetries of the n-cycle. So sigma and tau are as before. So sigma of x is x plus the residual class of 1, rotation, and tau is the reflection. Tau of x is simply negative x when we use labels from the set of integers modulo n. Okay, so we want to say every symmetry of the n-cycle is one of the elements that we proposed. We start with an arbitrary symmetry. And again, our main tool is going to be the rigidity that we have proved. We apply gamma to the point zero. It goes somewhere. We know that we can reach to the same point using a power of sigma. So gamma of 0 is simply sigma raised to power I applied to 0, where I is given by what gamma does to 0. Now, when I look at inverse of this applied to gamma, so this composite is going to be another symmetry of this n-cycle. Again, we are talking about the group of symmetries under composition. Both gamma and sigma to power I are symmetries of this n-cycle. Therefore, sigma to power negative I composed with gamma is a symmetry of the n-cycle. And this particular symmetry stabilizes 0. It fixes the point 0. It doesn't change. It doesn't move the point 0. We use the word stabilizes the point 0. So this symmetry fixes the point 0, but we described all such symmetries. If a symmetry fixes the point 0, then it is either identity or tau. So this is either identity or tau. Now again, we are interested in gamma. We single it out by multiplying both sides by sigma to power I. So by doing so, we get that gamma is either, in this case, gamma is sigma to power I, and in this case, gamma is sigma to power I applied to tau. This shows that every symmetry is one of these. Let's also point out that all these elements are distinct. Of course, sigma to the I applied to x is x plus the residue class of I, and all of these are distinct if I is in this range. And when I apply this to tau of x, I end up getting that it is negative x plus this. And of course, these are all distinct as well, unless n is 2. But if n is at least 3, then negative x is different from x, and therefore all of these are different, different symmetries. So from this, we deduce that the n cycle, the n cycle graph has exactly 2 unsymmetries. And we describe all the symmetries. They are coming from rotation and reflections. And notice that these are also reflections. These are order 2 elements. What do I mean by order 2 elements? I mean the following, that if I apply them again, like reflections, so if I look at square of these elements, let's see what we get. So I have to apply this to a point x, and I ask myself, what do I get? Okay, let's make it a bit thinner in order to take less space. So that means I need to apply this function to itself. Okay, so let's call this function f. Oops. So we are looking at f of x. That is f of negative x plus I. And I need to do it one more time. That means what? I have to negate, look at the negative of this quantity. And then add I. Okay, now negative of sum is negative of the first plus negative of the next. And then I get negative x. And then I have negative of I plus I. And as you can see here, negative x is simply x. And negative I cancels out I. So we end up getting x. And so f of f is just identity. Now, if you think about it geometrically, I have a reflection about this line, and then I'm rotating it. It would be a reflection by half angle. So it's a good exercise to see why this is the case. So these are all the reflections that we get out of the symmetries in this picture. So if I go back to the n cycle, so here we used this line and understood the reflection about this line. But of course, I can look at this line and think about reflections about this line or other n lines that we have, and we can take symmetries about those lines. And essentially, it's the same as saying that I'm taking this reflection and then rotating them one after another. And those are all these different powers that we are getting over here. Therefore, they are, when I apply them twice, it's like getting identity. So altogether, we end up getting these this precise description of all the symmetries of an n cycle. Now let's see similarities between this argument and what we had for symmetric group. By the way, symmetric group itself can be viewed as the group of symmetries of the complete graph. What do I mean by complete graph? Complete graph is a graph where I connect every two vertices. I start with n vertices and I connect all of them. For instance, in this picture, we see K5. We start with 5 vertices and we start connecting all of them together. So we get this graph that we call the complete 5 graph K5. Now, symmetries of this graph is precisely the symmetric group, because every vertex, every 2 vertices are connected to each other. In some sense, these edges contribute nothing, don't restrict, don't impose any restrictions on the symmetries. As soon as I get a bijection from the set of vertices to themselves, I'm automatically getting a symmetry of this graph. Now, the way that we understood how many elements symmetric group has is has a similarity with how we understood symmetries of the n cycle. And this is a common idea of finding number of symmetries of a graph. We start with one vertex. We ask ourselves, where can we send this particular vertex v1? Okay, we find out, okay, so v1 can be sent to this set of vertices. Often we can look at the degree of the vertices, or we can simply examine the shape of the graph to understand what other vertices look like v1. In the case of n cycle or the complete graph, the first vertex can be sent to any other vertex. But in some graphs, this is not the case. That would be the first thing that we do. We ask ourselves, where can we send v1? We find out how many other vertices look like v1. Then we fix v1. Then we say, okay, if I fix v1, the neighbors of v1 are supposed to go to themselves. I take one of the neighbors and I ask myself, okay, now where can I send this v2? Can it be sent? How many other neighbors of v1 look like v2, in the sense that if I fix v1, where can I send v2? To what other neighbors of v1 can we send v2? As soon as we find out how many of those we have, then we go to the next neighbor of v2. We continue like that. At some point, we reach to a rigidity. What do we mean? What do I mean by that? It means that we end up getting set of vertices v1, v2, vk, so that if we fix those, then we are fixing everything. Such a phenomena I refer to as rigidity. So if I fix these vertices, then the whole graph should be fixed. I should get identity. I cannot move it at all. So if a symmetry fixes this v1 vk, then it is identity. So when we reach to that stage, we simply multiply all the possibilities that we had so far. And that would be the number of elements of the symmetries of this graph. Why this argument actually works, the argument, the idea would be similar to the proof of symmetries of the n cycle. By the way, I forgot to mention, I wrote it, of course, you've seen it in the notation. The symmetry, the group of symmetries of the n cycle is denoted by d sub 2n. Maybe I wrote it over here. If not, let me make sure that I say it. It is, of course, on the title. Let's take this down and make sure that it is in the notes. The group of symmetries of the n cycle is denoted by d sub 2n, and it's called the n dihedral group. Okay, so let's summarize what we did in this video. We went back to the main motivation of defining groups, that means symmetries of objects, discussed this meta example of symmetries of an arbitrary object, and briefly mentioned why such a set forms a group under composition. Then we looked at the symmetric group of a set, where that set is just a set with no other extra properties, and therefore we get all the bijections from X to X. We discussed that this set under composition forms a group. We found out that this symmetric group, when X has n elements, has n factorial elements. Then we focused on the symmetries of an n cycle. We showed that rotation and reflection are symmetries of this graph. And we showed that every element is essentially sigma to the I or sigma to the I composed with tau. So we showed that the n cycle, when n is at least 3, has precisely 2n symmetries. And we described all the elements of these symmetries. The group of symmetries is called the dihedral group, and it has 2n elements. By looking at these examples, we mentioned this general theme of finding the number of symmetries of a given graph by looking at the first vertex, one vertex, and asking ourselves in how many other vertices look like the same as V1, using symmetries to how many vertices can we send V1. Then we fix V1 and ask ourselves, after fixing V1, where can I send a neighbor of V1? And we continue like that till we reach to a rigidity, meaning till we reach to a result of this type, that if we fix V1, V2, Vk, then I'm fixing the entire graph. In that stage, it's enough to multiply all the possibilities that we had so far, and that would give us the number of symmetries of the entire graph. Okay, so we'll continue and examine group homomorphisms and subgroups in the next video.